Good morning, everyone. Today is October 22, 2020, and lecture number 25, Digital MOS LSI Circuits, E524. In previous lecture, we have started with sequential logic circuits. In that circuit, we have learned the first topic of the chapter is timing matrix. In that, we have learned that various time related measures are there which are going to decide the specifications and the efficiency of your gates. One of them is propagation delay. One is setup time, hold time. As we are moving in like new era of high speed, jitter is also very important and it's affected at very high frequency, which is not given in book, but I talked about it and we study a bit about it. But if you are interested, it's a big topic and there are lots of books are available with this topic, and it's a really a big topic where you need to understand the random jitter, deterministic jitter, and lots of things needs to be done in this case. But we have studied only its behavior, how it looks. And of course, we already know what is the propagation delay. We already studied that when we are studying the inverter and the logic gates and other things. But we have also studied the setup time. In a setup time, let's assume that if it is a positive age triggered resistor, then with going from 0 to 1 of the clock, how much time before the D input should be available? So before the clock, it has to be available. That is known as setup time. And afterwards, how much time it has to be stable. And before that, it should not go to change its state. It's known as the T hold time. Notably, when you are doing this, and if you are having the D flip flop, whatever the time is required from going from D to Q, it's known as contamination delay going from C to Q. Sorry, contamination delay for going from D to Q. So such things we have studied. Other than that, we also have studied that there are, this is by the way the popular question being asked by all the companies for the digital. What is the difference between flip flop and latch? We know that latch is the one which is level sensitive and flip flop is the one which is the age trigger. I believe you know the meaning of this. And we also studied resistors. This is also a memory element, but this is called background memory element. The front end one is the one where SRAM, DRAM, and other memories are being made. And we also studied the static and dynamic difference between the static and dynamic, right? So static is the one which has, both of them would have clock, but this has the data which is stays static for a longer time, maybe like more than seconds or sometimes hours, sometimes days. But in dynamic, the data is changing in milliseconds, right? Static is like a pen drive where you store the data and then you look at the data that what is inside that. So such things we have studied. And of course, we have studied the most important part over here is flip-flop and resistors are kind of synonyms, but flip-flop is the one which is using the bistable latch cross-coupled structure, right? So if you are using this structure, which is of course a latch, so then it's a flip-flop. Note that it has to be age triggered. All the bistable latch cross-coupled structure are not flip-flops. They have to be age triggered or running with the clock. It has to be there. Otherwise, it will be latch only, right? So these are the things we have studied, and other than that also we have studied that there are 3 different points in a bistable property. So A, B, and C, 3 points are there, and we have studied that there are 2 characteristics look like this one. So C is the metastable point. B and A are the stable points, right? So if you have the point, if you are having the point C, means let's assume that I am giving VDD by 2 as an input over here. In ideal case, I am expecting here VDD by 2 and output of this one is VDD by 2. However, this is not going to happen. You might have some plus or minus delta change. That delta change will change these values, and after few iterations, like one after another one, what is going to happen? The output will be either 0 or VDD, or you can say that point A or B, which are the stable one. Those will be there. So that is what we have covered in the previous lecture. Now, let's understand one more thing, that there is a NOR gate based SR latch. You can understand that this is a latch because it's a level sensitive, right? So if set equal to 1 and reset equal to 0, we know that any of the input is 0, output is actually 1, right? So if this is the case, sorry, if set equal to 1, any one input of NOR gate is 1, output is 0. Any input is 1, output is 0. That is a property of NOR gate, right? So in that case, whatever the input here, it doesn't matter. This will become 0, and to get this 0, you need TP propagation delay, which is of this SR latch. If same propagation delay is here, this Q becomes 1 after 2 propagation delay, because there are 2 propagations are required going from one point to another point, right? So the worst case propagation delay is 2 TP, and you have to check the output after 2 TP. If you are checking the output before 2 TP time, you are going to see some misleading results that are not the correct one. That you should not see. Okay, so similarly, like if it is 1 and 0, same thing will happen, and the results will be flipped. This will become 1 and this will become 0. But the problem occurs when both are 1. When both are 1, both becomes 0. When both are 0, it's an invalid state that should not be considered, or we should make sure that such condition should not occur in the case when Q and Q bar are not equal, are equal. If they are equal, then it's not a good thing. You should avoid that state. So if you are designing such state, you can design with the clocked SR flip-flop. Note that I am calling it as flip-flop because it uses the bistable network, which is this cross-coupled inverters. You see, and along with that, we are going to have so we may have this kind of structure which is made up of CMOS technology. Now you can see that with different states, you can find out what are the values are coming. But when both are 1, means clock is 1 and S and R both are 1, you can see that both the outputs are going to be connected at 0, right? And that's an invalid state. We don't want that. But if one of them is 0, accordingly, like other state will be connected to the value. So here it will become 0 and here it will become 1. But note that all the things are depending on the propagation delay. So you need to check the propagation delays, right? And those propagation delays are in the form of the propagation of this inverter, and of course the propagation delay going from input to output side, right? So those are in this particular structure. You are going to have, so if R equal to 0 and S equal to 1, this is the thing which is going to happen, and Q bar will become 0. The other side will remain to 1 or it will flip to 1, right? Because this is 0, so this 0 input should change this to 1 after the propagation delay of TP. So propagation delay of each of these inverters are TP. So you will have the answer. And because of the cross coupled thing, you need to wait for not only for just TP propagation delay, but you have to wait for 2 TP on top of the available input, right? So these transistors will also get will give their own influence. Okay, so that has to be taken into account, and you know how to find out the Elmo delay, and that is the way to find out the thing. Now let's have one simulation where I'm giving the set value, which is this one, going from 0 to 1. Let's assume that this is what I'm doing, and reset is of course 0. I'm doing this, and clock is 1. Note that clock is 1, and this is a flip-flop which is running with the fact that clock is always on. Okay, so set is here, clock is on, so it will allow this particular branch in on mode, right? So this will be connected and other side will be disconnected. So we are expecting that this will become 0 and this will become 1. But all these things which we are writing here are the settled value. But what is happening in between, that we need to understand. So this value Q bar, let's assume that Q bar was at VDD, so that you can see the transition. Q bar was earlier time, like at the initial condition, it was at VDD. Q bar is at VDD at initially, right? And similarly, Q is at 0 initially. So what is happening over here, when it's VDD, to go to 0, it takes at least time, which is traveling from this point, like 0, going from here to here. It will take the propagation delay coming from these transistors M5 and M6 and the node capacitance over here, both the side actually. The capacitance which is available over here and capacitance available over here. So I'm not going into detail how you are going to find out, but C1 and C2 are there through which you can find out the delay. Elmo delay multiplied by 169 is going to give you the propagation delay. Or if you want to get the settling time exactly at 100%, you don't need to multiply with the 0.69. In this case, I am not going to multiply with 0.69 because I am interested in the settled value. So considering the settled value, this q bar is keep on going towards zero. You can see this q bar is going down towards zero as set is increasing, right? So when set is note that VDD is equal to 2.5 volt over here, and exactly midpoint is around here, 1.25, right? So the time when it reaches 1.25, it will make the transistor in on mode such a way that it can transfer the logic. So in that case, this q bar is going down, or you can say that little bit even before 1.25, it start conducting and q bar is going towards zero. So when this is going from VDD to zero, but not reaching VDD to zero, I would say that like this. And q bar was earlier at VDD and q is at zero. So what is happening to q bar? Little bit before this threshold, it start going towards zero. But what is happening when it's conducting? Look, till the time this is not going VDD by 2 or some certain value higher than VDD by 2, sorry, lower than VDD by 2, which is qualifying that as a logic 0. Until that time, this is not moving anywhere, right? Because if you are going from VDD to some value which is qualifying as a noise margin high, till that time this is q is remain at 0, right? It's not going to change. Look, even this value reflect q as 0 because there is an inverter, but it will start moving when I'm going in a region where it's almost like near VDD by 2, when this is going to start a little bit upside. So here you can see that there is some transition which is actually in the undefined state, and it start little bit going up. So if it is this one, so they are going to start in a different direction, and q will go to 0 and this one will go to 1, right? But that much time will happen. That will be, of course, this will be 2TP and rest of the things will also taken into account. So that we have to understand, and that's how the things will look like. And here you can see that TPQ bar and TPQ in total, it's coming from two inverters, right? Now let's go to the next level where 2:1 MUX is the important element to design a flip-flop, which is age triggered. Right now, what we have designed was actually a latch. Although its name is written flip-flop, but as we have agreed in this book, wherever you are saying flip-flop, it's the usage of two inverter back-to-back with clock as an input. So that is going to be called as known as flip-flop. However, with clock, if these values are changing, like when clock is high, during that time, it's getting set and reset also, like this one. And during that time, if inputs, this one is like this, which is reset. So during that time itself, you are going to see changes of Q and Q bar twice. So it's a latch circuitry which is the level sensitive. It's changing when clock is high. So we need to make the real flip-flop, which is going to work on positive or negative edge of the transition. So such things, if I want to design, then I'm going to use MUX, or you can say that the multiplexer, right? So generally, all people call it MUX, but however, the real name is uh, multiplexer. So 2:1 multiplexer is the one where you have two inputs. I'm not going into direct like the theory where there are n number of inputs, or you can say that better way is 2 raised to n cross 1, this one, and this side will be n selection line. 2 raised to n input, 1 output, n selection line. For 2:1 MUX, you are going to have two input, one selection line. Let's call this one as selection. Let's call this one as one is 0 and one is 1, and the output is output. What exactly this does, it says that when select is equal to 0, 0th value will be selected, right? This is already known to you. And when select is equal to 1, first value will be selected, right? So if select equal to 0 and at 0th position 0 volt is there, let's say, let's connect this one like this, then the output is 0, and select equal to 1, and if it is connected to VDD, VDD is going to be connected. So it's depending on what value you are connecting here, that decides this value, right? Sometimes you may have the bubble business also, so it's reverse of what you are saying. So when select equal to 1, which effectively acting as select equal to 0, so 0th value will be selected, and other things are already known to you, right? I'm not going into the whole detail how this is going to happen, but if it is 2:1 MUX, it looks like this, and the internal diagram look like this one. Or I can write down I0 and I1. So when select equal to 0, I0 will be the output, and select equal to 1, I1 is the output, right? So this is the known fact already to us. Now let's make the symbol out of this. Symbolically, people make such kind of symbol. You can make the square box also. People use this one also. But this is the symbol used in our use book. So that's Rabe. So let's do not deviate from that. So this is the selection line. These two are the inputs, and this is the output. So if I connect this select line to clock, and I want to make the negative edge trigger, if I am interested in making the negative, like whenever I would say that not latch, edge triggered, but if I am interested in finding out the negative latch, what it does, whenever there is 0 clock, value of clock of 0, then the output will be there. In other case, if clock equal to 1, the output will not be there, or it will latch the previous value, right? So what exactly is happening over here in the negative latch? In the negative latch, during this period, the output will be there on the level of this one. During the time when clock equal to 1, it will latch the last value which was available. Like in this case, this value will be considered. In this case, let's say Q1 will be there. In this case, Q2 will be, whatever the last value will be available, that will be latched, and it will not be changing until the clock is not going to change. So in that case, here there is a symbol where I want to make the same thing. So what I'm going to do, whenever clock equal to 0, you remember that whenever selection equal to 0, the 0th output will be at the output. So that is what we want. When clock equal to 0, at 0, if I am connecting D input, then that will be available at the output. However, in the case when clock equal to 1, I want to make sure that it will latch the last value. So I just do this one, right? And let's call this one as Q. So you can see that when select equal to 0 or the clock equal to 0, D is there. When clock equal to 0, Q equal to D. And when clock equal to 1, Q is equal to, or let's say Qt plus 1 is equal to Qt, or the previous state, right? Or it will latch that, right? So this is the way you can make negative edge, negative latch. But if you are interested in making the positive latch, it's the reverse of that. Just I am going to flip these two numbers. Instead of this, I'll make this D equal to 1 and this one is 0. What is going to happen when clock equal to 0? Q of t plus 1 is equal to Q of t, because it's coming here in this loop. When clock equal to 1, D and Q are going to be transparent. So that is going to happen. So positive and negative edge latch will be used. The usage of these two together in cascade, which is known as the master slave business, which we are going to use, and we are going to make the edge triggered logic, or you can say that edge triggered flip-flops, which might be static or dynamic. Static and dynamic latches are depending on the speed of the data coming at the D, right? So these are the negative latch and positive latch depending on the value of clock. And look at look here, the positions are looking same, but the internal values are changed. Note that. Okay, this is 1 0 and this is 0 1. So whenever you get stuck, you can make such thing and you can find out which is the correct one. Now let's understand what is inside this MUX. So I can make MUX 2:1 MUX, and note that I'm interested in finding out the positive latch. Means I'm making this one. When clock equal to 1, D is available at the Q, and when clock equal to 0, it's going to latch the value. That is what I want. So in that case, I'm using a transmission gate. Maybe I can draw that one more time so that we can keep the symbol also if you wish. Right. But this clock and clock path. Okay. Note that we have used a transmission gate with the fact that there is no drop, right? As you know that in the case of pass transistor, the value which is going that side is not going to be exactly the accurate one. When you are interested in transferring VDD, it's going to be VDD minus VTN. So to avoid that, we are using the transmission gate, two transistors in parallel, and these three are the inverters. Let's call them as I1, I2, I3. Okay, here following things are going on. Let's write down that. First thing is there are 4 transistors which are looking by the clock. So clock and clock bar is driving the load of 8 transistors, or you can say that when all are on, it's actually 8 times the gate capacitance, which is oxide capacitance driven by these. So 8 COX is a big number, by the way. Okay, because at the input you are going to see the oxide capacitance, and on top of that, of course, it will be some overlap capacitance also, right? So these are the overlap. I'm not going into so much detail, but we have studied that there are some overlap capacitances, and you are going to see the gate capacitance also. Now, when we are doing all these things, let's understand that when clock equal to 1, let's say clock equal to 1, as this is positive latch, what we want, when clock equal to 1, I want D equal to Q. So when clock equal to 1, you can see because of this bubble and because of this clock bar, these 2 transistors are in off state. Let's make them in off state. Whereas there is transparent value from D to Q. Note that when it's going from D to Q, on the critical path, I1, I3, and the transmission gate are coming into picture. So Q becomes D after the time of, you can say that it's equal to 2 propagation delay of inverters, because each one of them, I1 and I3, has propagation delay of TP inverter plus propagation delay of transmission gate, right? So this is what going to happen over here. But note that if you want to find out the setup time of this D, it has to be available before some time. Like when clock is 1, the data has to be ready before some time. That some time might be the propagation delay coming from I1. Okay, but we will look at that maybe at the later stage. But right now, this is the thing, right? And when it's a reverse thing, I would say that I need to when it's reverse one, this is going to be off, and at the same time this becomes on. Look at this. There is a loop. I'm removing the unwanted line. Right? So when clock equal to 0, at that time, clock equal to 0, this transistor, these 2 transistors are on. Okay, maybe for a better thing, I can redraw that. Right? So there is only this loop. The Q is detached from this side. There is no I1, there is no transmission gate which are on. So both are off. But when clock equal to 0, what is going to happen? When clock equal to 0, at that time, the data which was here, look at this, in this loop, again, there are 2 propagation delay from inverters plus TP of transmission gate. It's going to give me the output, right? Because I need to start from here. The starting point is here. So this was already available before making the clock off. When it's become on, the start point is from here. The data was here, the last value. Let's call this one as QT, and QT plus 1 has to go through the entire loop. when it's going through the loop, what is going to happen? On the critical part, there are two propagation delay coming from two inverters and one clock, right? So in total, this is also having such number, clock equal to 0 and clock equal to 1. Two things are happening. Now, as you know that these are the propagation delay or the output which is going from D to Q. You can also call this one as TCQ. It's contamination delay going from D to Q, right? So that will be 2 TP inverter plus TP TX, or another case it's 2 TP inverter plus TP TX. But if you are interested in finding out the setup time, because what is happening when clock equal to 0, I want to transfer this logic at that place. So before clock is coming, it has to be ready. So if you are starting from this point, your input has to be ready at least one propagation delay of your clock. So that this clock will be effective to send this data to that side. It does not require now TPX. It has to be available here, right? So that will be the setup time. And when this data is going to be like it's changing, let's say, or how much time is required for the whole time. This was acting as a setup time. This is acting as a hold time. So how much time it has to hold the data? Look, even if after this point, if I change the data with some delta t time, which is as good as 0, does not matter, right? If this data is changing, still that data will be transferred at other side. It's not giving you any kind of rule that you have to keep some time. So t hold is 0 here, or as low as 0 in the ideal condition. However, you can keep some value so that it will work, right? So this was all about the MUX based 2:1 MUX based positive latch. So where this loop is working, and you have to design all the things accordingly, otherwise things will be bad. So if I'm asking you that you have to make a system where I want the output at the rate of 1 nanosecond and clock is, let's say, of 10 nanosecond, then if I'm interested in seeing the output at every 1 nanosecond, in the worst case, then what I need to do, I have to design the propagation delay of the inverters plus the propagation delay of the transmission gate, all of them as lesser than 1 nanosecond or maybe equal, right? So that things will fall in line and you will get the output as you want, right? So this is what is required, and if you are interested in finding out the specifications such a way, you can derive it. Now, okay, as I told you, like at the beginning itself, the clock has to drive 8 times COX plus COLF value, right? Or you can say that the 8 times the gate capacitances, right? Let's call it CGB because that's the standard notation for anything. So 8 times CGB, which is a quite big load over here. So clock has to be reduced with the clock value. Why we are doing all these things? If you remember in assignment number 1, I have given you the inverter driving different capacitance load going from, let's say, 100 femto to 10 pico with some values of resistance like 50 ohm to 1 mega. We tried all these things. So it's all depend on what value of capacitance and resistance available at the output. So as these gates are being driven by the clock, which is created by maybe the cross-coupled latch, or you can say that from another latch circuit where clock and clock bar are non-overlapping one. If you want to create that, then it has to drive the load of some big capacitance, right? Which is generated because of this eight transistors. So it's 8 times CGB. So we need to reduce that. The reducing technique is only one. You can use a pass transistor based approach. So here it's similar, but the only thing which is changed over here is instead of these inverters, actually some of the inverters has been reduced. So here there are two inverters. In this case, it was there were three inverters. So circuit wise, this requires 6 plus 4, 10 transistors. But what we are proposing right now, it has 4 plus 2, 6 transistors. Clock, which is driving the gate capacitance, those are only 2. Right? So these are the capacitance they need to drive. In that case, things are pretty easy. Right? Now, let's understand how this NMOS latch works. So I know that QM is equal to, if it is positive latch, I'm interested in QM equal to D when clock equal to 1 and QM equal to the previous value, or you can say that it's in the latch mode when clock equal to 0. Now let's start with the 1 by 1 stage where clock equal to 1, then this particular connection is available and other connection, this one is off. Right? So this loop is not there, it's open loop. And when it's happening, what is going to happen? The QM is equal to D. It's a transparent one going from here to here. Because of two inverters, you're going to have QM equal to D. But after two propagation delay of coming from inverters plus the switch delay, which is the pass transistor. Altogether, you are going to have this. But in the case of QM bar, it's going to be equal to TP of inverter plus switch propagation delay. Look at this, it has one propagation delay of inverter is lesser. So you can have the output faster, but you can't avoid that. So you need to look at the output exactly after the worst case. So you need to sample the data after this one when it's settled one. If you are looking anything before that, it will be the faultier one because QM bar will be available, but QM is not available till that time. Right? So this is the one thing. Now, if it is okay, one more thing. Note that when you are doing this, if D is equal to VDD and D equal to 0, so there are two possibilities. If D equal to 0, there is no problem. This 0 is here and 0 is becoming VDD and VDD becoming 0. But if you are looking at different thing, which is VDD, which was the actually problem with pass transistor, that when it's going through the clock, it is VDD minus VTN, where VTN is the NMOS threshold voltage. When it's passing through this one, considering the fact that this is within noise margin high, then this is 0 and then this is VDD. If it is not within NMH, problems are there, right? So if it is deep submicron technology where supply voltage is less than 1 volt, this technique might be creating some problem. In that case, you can use this one as also transmission gate. The solution might be that one, right? But if you are looking at the pure transmission gate, pure pass transistor based solution, then this is going to happen. Now let's look at another condition when clock equal to 0, what is going to happen? So when clock equal to 0, this transistor is going off. It's detached from the output. However, The feedback loop is coming into picture, and this switch is on. So for that, you need two propagation of inverter to get the settled output. You might have the last input as VDD, and this is the output. In this loop, to get the settle as VDD, you need at least two propagation delay of inverter plus the switch propagation delay. So that might be used and you can have the output, right? I believe there is no problem in that, in analyzing this and keeping all these parameters as a propagation delay of inverter, propagation delay of switch, and all such things, right? Now, as I told you, till now, whatever we were making was positive latch. So these were the positive latch. Similarly, you can make the negative latch also by reversing the clock polarities. So then it will become negative latch. No problem. Similar thing, you can do it for the transmission gate. This particular thing is good for like in terms of having the lesser number of transistors as a driving value. So that way it's a good technique. But in these things, what is happening when, let's assume that I am talking about this is my clock. I am trying for the positive latch. Let's make this one as the top note that this is the positive latch, and if D input, I'm drawing something. So during this clock, if I'm drawing the Q, what is going to happen over here? During the clock bar, when it's happening, we don't care, right? During the clock bar, it is the latch value or the previous value. In between, if D is changing during the time when there is clock is on, then the output will also change. But I don't want that in a case of positive age trigger or maybe negative age, but I'm going to talk about the flip-flop which is positive age trigger. So I have to look at the transition only. At the transition within the setup and hold time, what is going to happen over here? The Q in the flip-flop, you're going to see like this, because here it's 1, here also it's 1. So within considering the timing matrix, if whatever the input is there, it's not going here and there. It will only take the value at the transition. So that is already known to us. That's the difference between latch and flip-flop. So if I want to make such system, what I can do, I can connect so when clock and both are clock, when clock equal to 0, I want that the output should go other side, means should be like this. If clock equal to 0, D will go that side, and in clock equal to 1, it will remain stable as we have understood over here. So in that case, this will be the thing. Let's call this one as Q1, let's call it D1, right? In other case, which is positive age, when clock equal to 1, I want that D should be connected at the output, and when it's 0, it's like this. If I connect both of them as kept over here, so in that case, the negative latch is given as, like, output of negative latch is given as input to the positive latch. And in total, it works as a flip-flop, right? This particular thing is known as the master-slave, right? So master-slave business is that in total, it's going to give you the thing as flip-flop, right? So here you can see that when clock is high, at that time, negative latch is not going to take anything, right? So it will latch. Here you can see that QM of the first stage is here. It's in under the latch thing. So whenever clock equal to 1, it's going to latch the previous output, right? But when the clock equal to 0, at that time you are expecting here QM equal to D. Here also QM equal to D. But when you are going in the next phase, when it's a reverse of what we are doing, so in that case, what is going to happen? It's a reverse of that. When there is clock equal to 0, it's going to latch, and this is for, by the way, Q2. So during this green part, it's going to latch, so it's not going to go here and there. But in the case of clock equal to 0, clock equal to 1, the latch output is going to be given to the output.